Hi, okay, so today we're going to do the addition of vectors with addition of forces experiment. So what we have is we have some forces. So what we're going to use for our forces is we have this thing called a force table. Why don't you just pan over to that quick? So what we have over there, and keep it on there. So we have some masses hanging from the table over pulleys. And so, as you know, weight is a force. It's mass times the gravitational acceleration. And so the weight of the objects hanging from those strings is going to give you force, and that force is going to become the tension in the string. And so you want to balance forces. And so now you can go back up here. And so forces are just vectors. So recall that a vector is something that has a magnitude and a direction. And if you want to add vectors, all you have to do is add them up. You can do it by adding their components, splitting them up into x, y, z components, that kind of thing. Or you can do it graphically by drawing the vectors and connecting them head to tail. So the first one is what's called the polygon method or parallelogram method if you're just doing two of them. And so you can see that in your manual, but basically what you do is you have a vector A. If you want to add the vector B to it, then you put the tail of vector B at the head of vector A. And now so this is B. I'll put an arrow over the vector to indicate that they're vectors. And so now we want to find the sum of the vectors, which we'll call C. And so all we have to do is we draw an arrow, a vector, from the tail of vector A to the head of vector B. So there's C. And the reason why we call this the parallelogram method is that you can also do it, well, you could draw something parallel to B here, and then if you added A to it, you would also get to the same point there. So you form the drawing isn't that great, but you form a parallelogram, which is a four-sided figure with two sets of parallel sides. And so if you have more than two vectors, then it becomes a polygon just because it can have more sides than that once you add more vectors. Give you an example of what that would look like. So we have A, we'll add B to it. And let's have C go back this way. And D goes over here. So adding all these vectors together, you just go from the tail of A to the head of D. And this would be, say, E, it's all of them added up. So you have A plus B plus C plus D equals C. So all this is manual. And now if you wanted to add them a different way, what you could do is you could take the components of the vectors. So if we're in the plane of the chalkboard here, then they would just have x and y coordinates. So let's say that A equals AX is represented by AX and AY, and B is represented by BX and BY. Then when you add the vectors together, they're like together. So all the x components add together and all the y components add together. So here we would have A plus B equals AX plus BX for the x component, and AY plus BY for the y component. And so that would equal CX and CY if we're calling the sum of the vectors C again. And so that's the vector C. Okay, so those are two ways to add them. And then we'll go through some of the math of getting the magnitudes and directions of resultant vectors. And I'll do that via an example. So peruse this if you want, pause the video, or look near. Okay, so now we're going to look at the mathematics involved in getting the magnitudes and directions of resultant vectors. So what I'm going to do is I'm just going to draw some vectors on the board using a ruler and protractor. So my first vector, I'm going to add three vectors together to make it a little bit more challenging. So I'm going to Well, this all depends on me leveling it to begin with, but I guess as long as I just draw the first vector in a line, it won't matter because I'm just going to put the protractor against that. So our first vector, we're calling that at 0 degrees. And so that's A. And its length, I'm going to try to get a precise value for the length here. Let's say 50 centimeters is what I want to get. So okay, so that one's 50 centimeters long. And the next one I'm going to do at an angle of 30 degrees to A, and I'll make it 35 centimeters long, let's say. Okay. Oh, I was doing, well, it's 30. I said I'd do 35, but I ended up doing 30. And let's make the last one at an angle of, let's say, 110 degrees to A, so that'll be 80 more degrees to B. And, oh wait, sorry, I did too many degrees there. 80 is over here. Okay, there we go. And let's make this one 40 centimeters long. Okay, so now I've drawn all of my vectors, and I'm going to do the resultant, which we'll call D. And we want to see how long D is and which direction it's pointing in relation to A being at 0 degrees. Okay, so what we do is we find the components for all of the vectors. So let's do A first. Now, so if the x-axis is, as usual, in the horizontal direction, then we can see that A is entirely horizontal. So it has an x component of 50 centimeters, I'm just going to write 50, and a y component of 0. Okay, now what do we do for B? So B has 30-degree tilt in relation to A. So what we do when we want to get the components of a vector that we know the magnitude and we know the direction that it's pointing is we use trigonometry. So we have, so for B, at some angle theta, so the x component of it is going to be equal to the magnitude of B times the cosine of theta. So for the magnitude of it, I'm just going to write B. And then the y component is going to be the magnitude times the sine of theta. Okay, so what do we have there? We have B is at 30 degrees. So the cosine of 30 degrees is square root of 3 over 2, right? It's been a while. So cosine of 30 degrees equals square root of 3 over 2. And I have to get a calculator to get the value for that anyway. 0.85. Yeah. Yeah, 0.866. Look, you're way off. So cosine of 30 degrees is 0.866. So we have, for the x component of b, we just have 30 times 0.866. And then for the y component, that's going to be 1/2. Sine of 30 is 1/2. Yep.
You want to show where theta is on the...
So this is the angle theta, 30 degrees. And then the angle here, or I should say the angle here is 80 degrees, which means that the angle of C to A is 30 degrees plus 80 degrees is 110 degrees. Okay, so we have, for the components of B, I'm just gonna erase the work that I just did here so that I can write it. Well, I'll keep the By, Bx definitions up there. So we have B equals 0.866 times 30 is 25.98. And 1/2 times 30 is, of course, 15. So that's components of B. And then we have C. So we want to do C in relation to A. So we want to do its angle in relation to the axes that we set up. So the total angle there is 110 degrees. So we're going to do the sine and cosine of 110 degrees. And just do that in the calculator because that's not one that you remember. Okay, so we have, I think this is in degrees. I'm just going to check it. Okay, looks good. So sine of 110. Okay, so sine of 110 is, I'm just going to write this up here to keep track, is 0.9397. And cosine 10 is negative 3.420. 3420. Okay, so to get the components of C, I'm just going to multiply 40 by 0.9397, and well, that'll be the y component. So for the x component, I multiply 40 by negative 3.342, and for the y component, multiply 40 by 0.9397. And so 13.68. And 37.59. Okay. And so these are all, so this is as if you would put all the vectors at the origin. Then if they're all like at the origin here, that would tell you that C was in the negative, part of the region of the x-axis. The fact that it's still like to the right of the origin over here just means that we've drawn it over there as we've added the vectors, but you can say that when you're adding the components together, it's as if they're all starting at the origin. You just add together all those components. So what here is just adding together. So D equals 50 plus 25.98 plus or minus 13.68. It's the x-axis, or the x component, and the y component is 0 plus 15 plus 37.59. So that gives us 7.98, 80, 62, 62.3, and 52.59. So these are our x and y components of the vector D, the resultant vector. And so now we want to get the magnitude and the angle that D is at. So I'm going to erase everything except the figure and the D. Okay, so to get the magnitude of the vector, for that you just use Pythagorean theorem, Pythagorean theorem. So we have magnitude of D equals 62 square root of the quantity 62.3 squared plus 50.59 squared. And so if we do that, you get 81.53. That's got to be centimeters in our original units of measure. And now we want to get the angle. So what do we know about the angle? We know that the angle, so we have an x component here of 62.3 and a y component of 52.59. So what can you do for that? Well, you use trigonometry again. So remember that tangent of theta equals opposite over adjacent. So if you find the tangent of this angle, then you take the opposite side, 52.59, divide by the adjacent side, 62.3. So if you have those sides and want to get the angle theta itself, then you take the inverse tangent of that quantity. So we have inverse tangent of theta equals inverse tangent of 52.59 divided by 62.3. And that gives us 40.17 degrees. Okay, so now let's check our work. So first I'll measure the length of the vector. And I'm getting, so 16 to 98, I'm getting 82 there. So that's very close to what I calculated. So measured 82. So we'll put a check mark next to that one. And now we want to measure the angle. And yeah, right on 40 degrees. So yeah, to the closest of measurement that I can get, right on 40 degrees. So both worked out very well. Okay, so that's what we're doing. So, a lot of abstract mathematical stuff here, but it relates directly to your forces that you're going to be adding together and trying to find the resultant. So now we'll move on to actually doing the lab. Okay. Hi, okay, so now we're going to do our force balancing on the force table. So we've already gotten a glimpse of this, and what we have here is we can do 3 forces on here. So we have pulleys and string. So what we do is we take a mass hanger. So these are 50 grams by themselves, and we would take one of those, hang it from here. Easier said than done. And then you can add more mass to it with these slotted masses. You can do that for each of the pulleys. So you get 3 forces. As we said before, the tension is just going to be the weight of the mass on there. Okay, so what we can do first, though, is we want to balance our force table. So this might not be balanced when you begin. So you take a bubble level. If you've never used bubble level before, you just have a bubble that you try to get in its window. So in this case, it's in a circle and start yet. I think people know what a bubble level is, but you can focus on it.
Turn it a little bit so you can actually see the bubble.
Can you see the bubble?
Focus on it. It's focusing somewhere else. Yeah, the bubble is near your index finger. You can see that.
Okay, so you see the bubble. So when you are balancing it, I mean, don't try to get over the table. You can just trust, that I'll explain it. So I'm looking to see that the bubble is inside that little circle in the middle. And so this is not balanced. And you simply have to adjust these legs to balance it. Oops, wrong way. Okay, and now I see that the bubble is lying right in the center of the level. So now the table is balanced. Okay, so now we are going to go ahead and set up our force table. So what they call for in the lab manual is they give you the mass and the angle of two of the masses, and then you want to balance it with a third force. So I'm going to start with, it says mount a pulley at theta 1 equals 20 degrees and hang a total mass of M1 equals 110 grams on the string. So I'm going to put this one to 20 degrees. It's closest to it right now. Okay, so we're going to now adjust the force tables, adjust where the pulleys are. So we want the first pulley mounted at theta 1 equals 20 degrees and hang a total mass of M1 equals 110 grams on the string. So if you can see the degree markings, do you think you can see it in there? Or just come over here, yeah. Okay, so you can see the degree markings on the side on the edge of the force table. So I'm going to move this pulley over to 20 degrees. Okay, and we want to put 110 grams on that one, so I'll go ahead and do that right away. So remember that the mass hanger itself is 50 grams, so we just need to put 60 more on there. So we've got a 50, 10. Okay, and then we also want to put the second pulley at theta 2 equals 100 degrees and hang a total mass of 180 grams on it. Okay, so 50 for the holder, so that means 130 more. So we've got 100, 20, 10. All right, so those are our two given forces. And now we want to adjust the third one. So I'm just going to pick a likely value. Let's say that maybe I need to add 200 grams to the pulley. We'll see how that works out, or 200 grams to the mass hanger. We'll see how that works out. Okay, so now that I've got this set up, you'll see that there's a pin holding that ring in the center. So if you release the pin, then you can see. So what you want to do is, never really explained this, is that if the forces are all balanced, then that ring is it's going to be in equilibrium, and that ring is going to move over the center of the table. Okay, so we're back to where we started. Let's not do 200 grams this time. So I'll start with 100. It's got to be too much the other way. Okay, so let's say I'll start with 150. Go, okay. So we're trying another mass now, so we've got 150 grams on top of the 50 for the mass hanger. So what we can do, instead of taking the pin out right away, we can note that the ring is touching the pin, so we know it's not quite in balance yet. So let's actually see if we can adjust. I mean, just by looking at it, you can see that the angle is probably going to lie more in here. So I'm gonna just change the angle around to see if I can make this look any better. So I've shifted it over where it looks like I might have the angle about right because the ring is now touching this side of the pin. So I just need to adjust the force a little bit more. So I'm going to add a little bit more mass to here. And if I get kind of close, I'll take out the pin again and we'll see how it looks. Okay, so that was too much. So let's take out the pin right here and see how it looks. Okay, it's actually pretty close. Just go do an overhead view. So we want to get the ring over that hole in the center, and it's pretty close right now. So let's say we add a 5. Add another 5. Now I know that that extra 20 was too much, so I should be at a point where I can add these 1 gram masses. Okay, getting very close now. Okay, right over the center right now. So let's write down what we got here. Just gonna write it on the back of this sheet of paper. So I've got an angle of 251 degrees. So theta 3 equals 251 degrees. Let's see what our total mass on here is. So I'll put the pin back on so that I can take this off and count it. So I had the 50 for the mass hanger, plus 100 is 150, plus 50 is 200, plus 20 is 220, plus 5 is 225, plus 5 is 230, and then 5 single, so 235. So I had 235 grams. M3 equals 235 grams. And now what we want to do, so we've got our result basically, but we also want to see what kind of range of values you can still get it to be centered, because due to some frictions in the setup, you probably, and just the small size of the masses, you can probably, like if you go down to the 1 gram masses, you can probably have some range of masses that you're still going to have it centered. So what we want to do first of all is adjust the mass up and down and just see what kind of ranges I'll get, so that I'm gonna define it as centered if the hole in the center is anywhere inside of the ring. So I'll take this out. And holes, maybe a little bit more. Hole's not entirely inside the ring. This is just my own kind of definition for what I'm considering balanced. This little 1 gram mass is barely change it at all, of course. Okay, I think the hole's now entirely inside the ring. So we'll say that that's our limit of being balanced. So I'll take off, well, I'll put the pin back on, and we'll see what mass we have here. So we had 150, 200, 220, plus 1, 2, 3, 4, 5, 6, 7. So 227 is our low value. And now let's see what our high value is. So I'm guessing, since I got it pretty well centered in the beginning, which was 235, so I'm going to say we're 8 under that now. Let's say that it's probably going to be 8 over that. So let's go up to 243 right away and see how that works. Okay, this is actually too much. It's lying outside the hole's lying outside the ring. of adding these masses. Okay, yeah, I think that's right about at the edge there. Yeah, we'll call it there. So this is our maximum value. Okay, so I've added masses until I got to where the hole in the center is just about lying outside the ring. So we're going to call that the maximum value. And I'm just going to put the pin back in so that I can count the mass. So we had 220 there. So this is the 225, 230, 31, 232, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 240 exactly. So our range is 227 grams to 240 grams. So if you want to get the mean value of that, you just add 227 plus 240 over 2. And I mean, it's technically part of your work, but I'm just going to do it because I need to mean value for balancing the angle. So that's going to be 233.5 grams. So we'll just say there's no half gram weight, so we'll just say 233. Okay, so I'm going to put 233 on there. Oh, it's not lying on the pulley. That was the issue there. Still is pretty uncentered though. Maybe it's just swinging too much. Yeah, so what I just saw there, and I wasn't even trying to do this, but just by taking the masses off and putting them back on, it caused it to center much better. So you can see that, you know, I applied some force when I was just touching the hanger. And, you know, in theory, that shouldn't cause it to center somewhere else than it did before. But since there is some frictional forces in here, that's why we're doing this kind of range. So now it is centered well. And with using 233 grams. Now we want to adjust the angle to see what kind of range of angles we can keep it centered. So I'll just slowly move it to the side. It's way too much. It's going to be a pretty narrow range. Okay. So I've got 253 here. So 2 degrees to one side. Let's just try 2 degrees to the other side. Okay, 3 degrees to the side worked on this side. Let's try 3 degrees to the other side. And it's a little too much on this one. So it looks like our range is from 248 to 253. So once again, you can calculate the mean value of that, and we'll provide you with all of these measurements. So our mass is between 227 and 240 grams, and our theta range is between 248 and 253 degrees. And so what you want to do is you want to then Well, let's see what they actually have you do in the lab, because I think that they want you to just confirm mathematically using that kind of analysis that I did, confirm that that the components of this third force, F3, that you get are what you would have expected from the two forces that you're adding together, and the direction as well. So you want to confirm that. And then they also want you to draw it on graph paper so that you can confirm it graphically as well. And so that's the lab for today. And the rest of it is the analysis and answering the questions.